So my name is Yuandong Tian from Meta AI. Meta is previously known as Facebook. Now they changed their name. I'm a research scientist and also manager there. So today I'm going to talk about AI-guided surrogate modeling for real-world optimizations. I changed the title a little bit to more faithfully reflect the content of the talk. Okay, so I previously was working on reinforcement learning and still working on reinforcement learning. And reinforcement has been very successful in many games, right? So people have already seen a strong success in Go, chess, Song, and I think yesterday actually DeepMind actually gave a talk in how to apply an AlphaZero kind of approach for alpha tensor and to get interesting solutions. That's the applications. From our side, we also have a reproduction of AlphaZero back in 2018 that tried to basically use 2,000 GPUs to train a strong Go model. That model was actually beat 4 different professional Go players with 20-0. They didn't get a chance to win a single game. And on our side, we only use a single GPU at 50 seconds per move. But after that, people have been working on these games again. We see a lot of superhuman performance for different games, right? So now let's think about what is beyond games if we use reinforcement learning, if we use any kind of search technique, right? So one thing that actually is kind of motivation of this direction was actually the chip design work from Google, right? So in that paper, I mean they show that it's possible that to reduce the several weeks of the human expert work to full ultimate design in 6 hours. So this actually gives us this kind of inspiration that maybe you can apply any kind of search technique or optimization technique or reinforcement technique to optimization problems. Right, so for all these optimization problems, we actually have a well-defined function f to be optimized, minimized, or maximized. And you really want to find a way to solve these problems, right? So people may wonder, oh, wait. So this seems to be not possible because many problems are actually NP hard. Okay, why? And you can prove there's no good solutions unless P equals to NP, which is highly unlikely, right? So, but why machine learning or any kind of learning technique can actually help for these problems, right? So I think one theoretical argument is that these guarantees are worst case guarantees, which means that in order to prove a lower bound, you really want to construct some very specific examples, some adversarial examples, so that any algorithm, some specific algorithm will fail to that specific lower specific problems, so that you can prove that for any for this kind of family of problems, and there's no way you can find solutions in polynomial time, right? But this kind of proof actually give you kind of insights, right? So maybe for specific distribution of the optimization problems, there might be better heuristics, right? So that's probably the reason why, in practice, humans who play with the optimization problems always can find an interesting heuristic that is working very well for specific distributions. Yeah, so that's basically the intuition why we really want to leverage machine learning for solving this problem. So if you think back to the game side, I think about how can we leverage this game paradigm to optimization. So we think about if we come back to the game, we actually think about how can we in games what's happening is that we actually replace human knowledge with the machine learning models, right? So for example, we replace the choice of actions with a machine learning model called policy network. We also replace the evaluation of the ball situation with machine learning models, which is the value functions, right? And we basically can leverage that in order to get faster and good solutions in a short amount of time. That's basically the motivation. But in order to think from the direction of search, then there's a lot of component in search that can be replaced by machine learning models. Right. So here I basically list maybe a few different components that can be replaced or can be improved by machine learning technique. Right. So for example, you have the search heuristics. So in that part, we actually have a lot of work along that line to improve the search heuristic in order to get like a better solutions for hard optimization problems. Right, so we have our original starting work from this learning to rewriting paper that is published in Europe 2019 that tried to learn this rewriting heuristic, how to improve initial solution gradually until it becomes better and better and getting like even better solutions than the previous approaches. And we also have recent work that tried to apply reinforcement learning network planning, which is a large-scale mixture interlinear programming problem to find initial solutions for the mixed interlinear programming. And initial solution can be used for solving this mixed interlinear programming much more efficiently. Right? And we also have our recent work by Taiwan in this workshop, try to using contrastive learning in order to learn the heuristics for large neighborhood search. Right. So that direction is by itself a very fruitful direction that we can try in order to incorporate machine learning for optimization. Okay, so we also have another direction that is also an angle that you can attack by using machine learning models. So here's like one simple example that tried to tell you how we should formulate optimization with reinforcement and kind of sequential decision-making process. Right? If you think about optimization as a search technique, and you probably want to think about like how we can do a sequential search in order to make to find good solutions. Right? But for one optimization problem, there may exist a numerous way of constructing that as a search problems. Right? It's possible that if you don't construct that well, then you are basically screwed at the beginning. Right? So here's like one interesting figures. The figure basically says, okay, you construct a sequential decision-making process so that at the beginning, the action doesn't really matter. Okay, you can choose any of them. You suppose like you have 50 first actions that you don't really need to think about. You just do random choice. And in the 51st action, that action really matters. Okay, if you pick the sequential decision-making process like that, then any approach, any kind of search technique will get stuck in these kind of scenarios because it has to first explore the first 50 actions and expand the entire tree in an exponential manner until you really touch the action that really matters. Right? So for these kind of scenarios, any kind of search technique, any kind of reinforcement technique won't work that well. Right? But if you basically like swap your action a little bit, you say, oh, I really want to use that important action first. You pick that important action first, then all of a sudden the problem becomes trivial, right? So you can just reduce it to a bandit problem. You have started with like good action, and then good action will tell you where we should go. For this one, we actually also have a bunch of work that try to rearrange the action space so that the optimization problem becomes easier. Right? So we have this ARMCTS series that try to basically learn the action space for Monte Carlo tree search in order to solve optimization problem faster and more efficient. Right, so recently we also have an application in the compiler optimization problem that to rearrange the actions to first learn a sequence of important useful compiler paths so that that compiler path can be useful for reducing the code, the size of the resulting binary code. Yeah. And the third part is like we can also try to learn the state representations. Right? So here's like a small figure that in one of our papers that try to explain why there's a lot of like irrelevant features in the state representation. Right? So here's basically like a very simple macro decision process. You wake up, you open your window, and you want to basically get more sunlight. Right? So, but you see a lot of things in your eyes. Right? So you see like sun, you see like airplane, and you also see like a bird chirping. So in that case, like only a very small subset of your state space it really matters for your decisions, right? So what really matters is that you can touch the curtain and then move things around, and that's something that's controllable. And also, once you move the curtain, you also get your rewards, which is to let more sunlight in, right? But there's a lot of other information in your state that doesn't really matter, right? So you really want to decompose the state so that only the most important state is involved decision in your machine learning models. Right? From this, we also have a bunch of papers along their directions. And finally, this is the topic of my talk today, is the final component, which is to how you design the surrogate models in order to learn to basically accelerate your optimization process. Right? So people may wonder why we want to learn surrogate models. And this is because, first of all, in real-world problems, it's very slow to evaluate to evaluate the real systems. Right? So for example, you want to optimize your recommendation system. It takes a day to get one single feedback. Okay. If you just try any online approach, you're basically doomed. There's no way you can basically get solutions and get your feedback very quickly. Right? And second is that your final optimization, the final results of the model may be super noisy. You really want to find a surrogate model that gives you an accurate prediction. So for this, it's also a hard problem. So how can we design surrogate models is a big issue. So for this, we also have a line of work along that direction. So I will not have time to cover the first two, which are also very interesting. But today, I'm going to talk about these two work. So one is a collaboration with Bistrot's group on how to learn the linear surrogate models for nonlinear combinatorial optimization problems. And the second one is also our collaboration with our product group that try to basically model the dynamics and also model the frequency response of linear partial differential equations in order to accelerate the search and design problems for antennas. Okay, let's start from the first problems. Right, so this is, as I said, it's a collaboration with USC and also Rice and ourselves. And for this one, we basically know that the setting is we want to optimize nonlinear functions over combinatorial regions. Okay, so here's a small figure, right, showing the extent of the settings. So your optimization function can be highly nonlinear, right? So the landscape is a weird shape. We don't really know what it is. But you also have a nonlinear constraint. Right? So this setting is actually very universal in many different scenarios because it's actually applied to many real-world domains, including computer system planning, designing photonic device, right? So throughput optimization, etc. Right? So here's one example about that. So this is actually a real-world example that you can take from a training of large models, not necessarily language models. And so here, basically, that's called the embedding table placement problems. So in that problem, from a mathematical point of view, what it does is that you have k tables. Okay, they are basically the embedding tables. And you need to basically put these k tables into n identical devices. So these devices means GPU. Right? And then in order to place that, you basically have a constraint. The constraint basically says, oh, this table I has memory requirement, mi, and each device has capacity. Right? You want to place the table so that the number of the memory requirements, if you sum them together, each of the table, each of device does not exceed the memory capacity of that device. Right? And at the same time, you want to reduce the latency to compute all the tables. Yeah. So that here's basically the formulation. The formulation basically is that you have kind of a binary constraint. This xij means that you want to assign the table I to device j. Right? So, and you basically say that each table I has to be assigned to only one device. That's basically the constraint. And this is the capacity constraint, and you want to minimize some functions so that the entire process is done in an efficient manner. Right? So why this area is nonlinear? Because there's a lot of system issues. Right? So for example, the GPU has kind of weird property of batching. Right? If you put multiple tables in the same GPU, they can execute it in a faster manner. Right? So that's kind of nonlinear factors. Right? If you place multiple tables to multiple GPUs, when they reduce everything, you need to have a communication cost. This is also a nonlinear problems. Right? So because AI is nonlinear, so this probably makes this entire problem complicated, and it's not really a ready problem for the existing solvers. Right? That's actually a big problem. So what previous work is focused on is try to linearize the error. Right? So you say, okay, let's do linearization of the objective functions, and then the linearization hopefully can give you good solutions. And then you can do these things like back and forth. You say, oh, let's tweak all these weights a little bit, and then you get some solutions. And then maybe the solution is not great. Okay, let's tweak the weights a little bit more, and you get solutions. Right? Do this iteratively. Okay, so for SurCo, we actually try to make this entire process a little bit more automatic. Yeah. So we all know that the linear optimization is hard because usually the general solver is often slow, and for specific domain, it may have specific solvers. Right? So there exists like a nonlinear optimization problem that is very general. Right? For example, genetic algorithms, gradient approaches, but these approaches are usually pretty slow and may take forever to get feasible solutions, or not even be able to get any feasible solutions.
I'm sorry. What do you mean with feasible solutions? So feasibility shouldn't be so difficult. I guess the objective function, optimality.
Yes, that's right. So if you get rid of these nonlinear functions, you just call any linear solvers. For this one, it should give you a feasible solution very soon, right? So what I'm saying here is that if you just apply genetic algorithms or any kind of gradient-based approaches which does not have a feasibility check, feasibility like a mechanism built in, then you might not be able to get feasible solutions very soon. Yeah, that's basically the point. Yeah. And we know that in contrast, linear optimization is somehow easier because we already have a lot of solvers that are able to solve these problems, right? So then we basically want to propose this tech idea called SurCo, which actually aims to find a linear surrogate so that the solution of the linear surrogate actually matches the solution of the original nonlinear problems. Okay, so maybe the logic is a little bit convoluted, so I want to repeat and say what's the actual logic. So suppose you have the nonlinear optimization problem with combinatorial current constraint, which is this one, right? So you really want to use that one, and you want to predict some surrogate cost. That cost, once that you plugged in that cost to a linear surrogate optimization problems, the solution is basically the solution will be useful for optimizing the original non-linear optimization problems. Okay, so that's basically the logic of SurCo. Do we have any questions?
Why is this possible?
I think that this is definitely, there's a lot of limitations for these assumptions, right? So for example, one obvious limitation is that if the optimal solution is in the interior of the feasible solution, then it's not possible, because if you just make it linear, then it has to be on the vertex.
Unless your linear approximation is like the convex hull of the integer points or something.
Yes. Yeah.
So, do you have any assumption over the objective function? So this latency is convex, for example?
No. There's no.
It's not convex.
Yeah. So here in this paper, it's mostly an empirical paper. So which means that we actually tried this approach and actually works in real world problems, and we have very simple theoretical analysis, but it's still out of the scope of this paper to do a very thorough theoretical understanding of this approach. Yeah, so I think the one obvious limitation is that if the interior has the optimal solution, then you won't be able to get it, right, for this kind of framework. But interestingly, if you actually really try it in real-world problems, you actually see pretty good performance in many different scenarios. That's the point of this work. Okay, so then if you think this is a good kind of settings, then the next question is how can we find the right objective? Right, so how can we find this kind of surrogate cost C in order to get these solutions? The proposal is to use gradient-based optimizations. Right? So you have this kind of pipelines. You know, okay, you want to first get a surrogate coefficient C so that the output, the solution X star, is the solution of the objectives. Right? So how about we just do backpropagation all through, right? So you want to say, I just want to minimize this loss function. And this loss function and the X star is provided by the linear solver, right? So and then we want to basically do backpropagation through the objectives and also through the solvers in order to get the surrogate coefficient C. That's basically the rough idea, right?
But, sorry.
Yeah.
Can you not underestimate? Can you not get something that's how do you guarantee some of the loss function doesn't use any ground truth optima or anything? So you're just finding a C which has a low value.
Yeah, that's right. So so that's basic. That's why we have 3 versions of that of that problem of that method, right? The first one is called circle zero. I mean, the circle zero basically say I just want to solve one specific objective functions, right? So you just have this fx, and you want to solve it. You do backpropagation, then you will get a surrogate coefficient C that will lead to the optimal solution of that particular nonlinear optimization function C, right? So that's function f. I mean, as you said, yeah, that's true. You can get into some very specific coefficients that lead you to the optimization, the solution to the optimization problem. But that one is not generalizable. That's totally possible. Yeah. I'm not sure if I answer your question correctly. Cool. Yeah. That's one way of doing that, right? But you can also think about maybe a different way. So okay, we go through this process and we only get one solution, which is the x star. How about we have another problem with very similar settings, but slightly different objective functions? In that case, we actually propose called circle prior. In a circle prior, we also take these problem features in mind. So this is kind of called context features, right? That feature will be useful for determining what are the loss functions we're actually optimizing, right? So you have a function f you want to optimize with respect to your variable x, but that function f is also parameterized by the problem features, right? So you really want to learn a solution that is also parameterized the problem features. So how can we do that? So we can actually do circle prior. So in a circle prior, what happens is that you still have these 2 blocks, right? So the solver, the objectives, but now the surrogate cost C, the surrogate coefficient C, is not a standalone variable, but is actually a function of the program features, which we know beforehand. And then we do backpropagation all the way through. Then instead of learning the surrogate coefficient C in order to get optimal solution of the nonlinear problem, we actually get a neural network. That neural network is to map the problem feature Y to the surrogate coefficient C. Right? Because of this neural network being learned, in the new problem, for the new problem with the new Y, new description, we can directly plug in this problem feature Y, and that neural network will give you directly the surrogate coefficient C. And that C can be useful for solving the optimal solution of the new problem using the linear surrogate optimization. Yeah. So that's basically what I said, right? So once you have trained this neural network, then during test time, you can basically plug in your problem, test problem description, and that will basically give you the coefficient C, and that coefficient C will be useful for calling this linear solver and to get a solution, which is the x star for the original non-linear optimization problems. Okay, so of course we can combine the 2 together, right? So we can say, okay, how about we first learn the linear network mapping from problem description Y to see what is the main content for the circle prior in the previous slide. We can also use that C as the initial surrogate coefficient C0. And then we can try our circle 0 on top of this initial surrogate coefficients to further improve the quality of the resulting solutions. Right? So it's basically, this hybrid is used to combine the circle prior with the circle 0. Then you get something that is even better in terms of the final results.
So then, if I assume correctly, you do this during the test time, right?
Yeah, so this one, you do this in the test time.
Okay, and then in that
Sorry,
case,
I think I should use this one, yeah. Yeah, so this is basically what you do for the test time.
Right,
yes.
but then in that case, why do you care about the last gradient step?
You mean this one?
No, go back to the
Yeah.
Yeah. So like the 3 blocks, the blue blocks that you have there.
Yeah.
As far as I understood, you have an initial C, and then like what I'm trying to understand is that why do you have the parameter theta updates here as well? Like you don't care about theta anymore, right?
Oh,
This is like test time. You got a good theta, and it works well. And
Yeah.
with that theta, you can get initial C0.
yes.
And then, like, why don't you just like do the back props on the last 2 blocks there? Like, why do you care about updating theta at test?
Oh, I see. Sorry, this is a typo. I should remove that block. Yeah. So I think okay, I just did copy and paste. So yeah, this block should be removed. So what we do is that we first do this C0, and then we just do backpropagation of the two blocks. So the last block should not be there. Yeah. So sorry for the confusion. Yes. Okay. So I think that here's a summary. The summary is that for circle 0, what's happening is that you have these 2 blocks to optimize. 2 blocks to optimize, and then you do backpropagation. You don't need any offline train data. You just optimize that specific function f. Right? Just solve a single problem instance on the fly. And for circle prior approach, we actually use offline train data. Right? So we have a train data that consists of a bunch of problem descriptions. And then we basically run this in a batch manner in order to learn the neural network, and then use the neural network to get the C test in the test time. And in a circle prior, in a circle hybrid, we basically do both. Right? So we basically do offline training and also on-the-fly fine-tuning for the surrogate for the new problems. Again, as we discussed, like, this block should not be there, right? So I should remove this. So this approach actually has a lot of connectivity with the previous works, right? So I basically here we list a bunch of related work there. I think one interesting comparison between SurCo and the recent series of work on predict and optimize is the following, right? So if people have been trying to do this predict and optimize kind of a paradigm in which you would basically want to say, in order to predict the linear cost for linear problems, we don't want to use L2 norms, but we want to use some norms that's related to the optimization problems. Right? So there's a difference between SurCo and this predict to optimize kind of approach. First of all, the predict to optimize approach is suitable for linear optimization problems, right? with linear objectives, but we are actually suitable for nonlinear objectives. And for the predict to optimize actually requires a ground truth linear coefficients, CIs, for the objectives. Right? So, but in our case, we actually don't want that. So our training set only requires the problem descriptions. We only have a list of problem descriptions there. There's no need to provide the algorithm with any optimal solution or the linear coefficients. Right? So the algorithm will try to figure out by itself. That's basically the benefit. And in our case, we are suitable for nonlinear objectives, and that nonlinear objective only need to be propagatable, right? So as long as you get a gradient, you can try this approach. There's no need for any analytical form for that linear objectives. Right? This is basically in contrast with existing nonlinear solvers with combinatorial constraints. For example, if you try nonlinear solvers in like skip, right? So they actually requires you to write down the analytical form. Right? You have to write a log, exp, polynomial forms in order to construct the nonlinear functions for them to actually find the upper and lower bound for that function to do a branch and bound. But in our case, we just do gradient descent, so we don't need any analytical form there. Yeah. Of course, both requires contextual information like the program descriptions. Right? Otherwise, this is the minimum requirement for solving this kind of problems and extend it to unseen problems of the same distributions. So we also see a lot of other related works, and many of it are actually provided in this community. And thanks for all this work, and that actually triggered our thoughts and leads to SurCo project. So then, let's go to basically proceed to talk about our final results for these 2 problems. One is called embedding table sharding. That's actually the real problem in training neural networks, right? I mean, more specifically, this is basically useful for training our S models. It's public, so I can say that. So this is basically the optimization problem we want to address. As I mentioned, you have a nonlinear problem, error, and you have a linear constraint here. right? And we basically like compare this with multiple baselines like greedy. Like I also compare with this reinforcement learning-based approach called DreamShot. This is also our work that is being published in Europe. Right, so we basically check like the results, right? So basically here the x-axis basically this benchmark, this benchmark called deep learning recommendation models, right? So, and it has several parameters, right? So first of all, how many tables do you have? So this is like 10 to 60. That's the number of tables that is listed in the x-axis. So you have DRM 10 all the way to DRM 60. And it's all like placed at like 4 GPUs. Right? So you basically have two comparisons. One is like how much is the solution loss, right? So you want to minimize the solution loss, right? To minimize the function. Of course, the lower the function, the better the solution is. And secondly is like in order to achieve that performance, how much time you should be involved in terms of getting the solution, right? The runtime. You really want to have a lower number in the runtime and also lower number in the solution loss, right? So it's the lower the better. That's basically the settings. So if you check like for very small scale problems, right? So for example, you only have 10 tables, and you will see that if you compare with the domains heuristic and greedy, the SurCo 0 actually does reasonably good job, right? So it actually have pretty low solution loss, and at the same time, the speed is reasonably slower than the heuristic, but actually is faster than greedy and also and reasonable, right? So if you try, for example, the SurCo prior is very fast, right? So it basically does not have a lot of runtime because you only need to solve the optimization problem in one shot, right? With the predicted C, and at the same time, the loss is not that bad. I mean, it's still reasonably good, right? So that's the interesting trade-offs. If you scale things up to, for example, larger and larger scales, right? You have 60 tables. And in that case, what you really see is that you can see like we actually have like a higher advantage, larger advantage there, right? So for example, for the SurCo 0, the SurCo 0 problem basically it gives you like very small solutions or very good solutions. The loss is lower than the two approaches, right? So that's the domain heuristic and also greedy. And also, it's better than our previous work called DreamShot, which is actually reinforcement learning in order to get good solutions. Right? So that's interesting that with the solver, it actually gives you better solutions there. Right? So if you combine this with, for example, SurCo prior and you get a SurCo hybrid, then you can even get better solutions. Right? So the loss is even lower here. Right? And of course, if you only use SurCo prior, then the solution is not as good. But it's much faster. Right? This is like you see like a much faster runtime. So there's a trade-off. And in practice, when you actually want to use this approach, you can always like make a trade-off between using the prior solutions and also using a fine-tuned solutions. So you can, for example, constrain the number of iterations in the optimization steps during your deployment in order to make this trade-off. Okay. So this is the first application. The second application is called inverse photonic design. That's another application. It's actually an interesting application for the material design problems. Right? So for this one, the goal is to design physically viable devices that take light waves and roll them to different paths. Right? So it depends on their wavelengths. So this is kind of like a small device with like, for example, 100 by 100 nanometers, very, very small device. And then you have lights coming from above, right? And you basically, what you want is like you really want lights to go to different route, depend on their wavelengths. So for wavelength 1, you want the light to go that way. For wavelength 2, you want the light to go this way. So that's basically the goal of this kind of device design problems. People may wonder, okay, why not use a reflection, use some mirrors for this problem? But it's very hard to put mirrors in this very small space. So you have to basically use the electromagnetic wave properties, diffraction properties in order to separate these two wavelengths. Right? So that's the goal. The goal is to basically, okay, here's like in terms of optimization problem, what's happening is that you have this is a binary image, right? So it's from 18 by 80 by 80. Binary images. For every location, there's either a 0 and 1 design variables. whether you put some material there or you leave it blank. And by like adding different like design materials, then it will change the electromagnetic property of that small piece so that the light, when it goes from the top, will basically actually split into two different routes. Right? That's basically the design problems. Yeah. Any questions? No. Okay. Yeah. So for these design problems, you have first things are binary. I mean, obviously every slot you have to be 0 and 1 is binary. And second, you also have constraint. That constraint basically says you don't want to have these blobs to be too small, right? So you want the blobs to be has some minimal size, like some kind of maximum size, some minimal size, right? So basically, you don't want like a very single like one dot that is isolated from everyone else. That's not allowed because it will pose problems for manufacturing. So then there's some linear constraint you can impose for the design problems. And the objective function is complicated. So here's like crazy objective functions. And we don't understand because this domain, it's basically provided by some domain knowledge, some domain experts. I want to basically say, okay, I want to minimize these functions for whatever reasons, but I want to minimize it. Yeah. So we actually use the data sets, actually is already public from Google. Right? So actually one of our courses is actually from Google. He's now in Meta. Yeah, so, and we also try to compare this with the brush-based algorithms, right? So there's a lot of algorithms that are designed specific for that particular domain to get any solutions there. And we are trying to leverage a general approach in order to show whether our general approach can do better jobs. And we also evaluate that on multiple tasks, right? So here, there's a bunch of different tasks in order to test the performance of the algorithms. Right, so for example, here you are trying to basically bend the wave from left to right to go in top. Right, so you also want to basically convert the mode, right? So from one beam to two different beams. So there's several different way of constructing tasks. There could be more tasks later. So here's the results. Okay, so the result basically show the same trend, right? Similar trend for SurCo 0. It gives you a reasonable performance, better than the existing state of art. So this is a pass-through gradient approach. It's also gradient descent approach, but does not involve any combinatorial optimization component, right? So it's basically doing gradient descent, but project the results onto the feasible regions. I do this intuitively, without using any kind of existing solvers. But our approach is able to getting a better solution loss. Right, so and at the same time, if you use SurCo prior, you also get much faster runtime. Right? If you use SurCo hybrid, then you get a lower solutions loss at the same time, relatively faster runtime. You can also try to do the same thing for other kind of settings. Right? So I didn't want to spend too much time on all this. I mean, so for these two are maybe too simple. So most of the algorithms give you 0 solution loss. You don't. That's great. That's the hardest is basically the beam splitter and also the multiplexer. Okay, and here basically like one of the curves that is shown how SurCo can converge. Right. So for example, if you use this pass-through gradient approach, I mean you see over different steps the curves goes down, but it's very noisy, and it may not touch like 0 in terms of the final solutions. And if you try to use SurCo like zeros, and you see like the curve grows down much faster. If you use SurCo hybrid, it goes even faster because it starts with a good starting point of the surrogate cost. Right, so that's the kind of like very good illustrations why the SurCo paper, the SurCo can work. Yeah. Okay, so that's basically the conclusion of the SurCo paper, right? So in summary, it can handle industry-level applications with differentiable optimizations. They give you good solutions to combinatorial nonlinear optimization problems, which is actually has a lot of coverage in industry-level problems. Right? So and the SurCo have different versions. We have 3 versions. We have 0-shot version called SurCo 0. And we also have an offline training version, a fine-tuned version called SurCo prior and also a SurCo hybrid. Okay, that's the first part of the talk. Any questions? If no questions, then I will continue with the second part of talk. So this is another work that I've been collaborating with our production team on the designing of antennas. So for this one, we're trying to build a surrogate model for frequency response of linear partial differential equations using self-attentive complex polynomials. People may wonder why there's polynomials. That's kind of mysterious. But you will see why it happens in the next few slides. So here we are talking about different problems, try to solve linear partial differential equations, right? So you basically think about this kind of like equations, right? So you think about like here, you have some spatial temporal signals, right? So this can be kind of electromagnetic waves in the space, and how it can evolve over time, right? So it can be electric field, magnetic field, any kind of like a continuous field quantities, right? And then you basically want to solve this problem. So this is this is a linear partial differential equations in which f is a linear function or affine functions that take the signal itself and also the gradient of the signal and the higher order gradient as input, and do some linear combinations. And this combination will affect how the signals evolve over time. So that's basically the linear PDE that we are addressing. Right? And this H is the design choice we want to put into the system so that the evolvement is following what we want it to be. Right? So there's a lot of examples for this kind of formulations. For example, heat equations, wave equations, and even like Schrodinger equations. I mean, these equations, it's still a linear equation because it only, in both sides, you only see like the first order term of phi, right? So in both sides, that's the, and there's no second order term. There's no like phi square or any kind of nonlinear interactions between phi and itself. Right? So you also have Maxwell equations that will have the same properties. Right? So you only have E and B, which is the fields. And all the rest of the terms, they are basically linear with respect to E and B. So usually what people do is that in order to find a good design to satisfy any kind of requirements that we want, usually we want to simulate these partial differential equations. Right? So we can call any kind of like commercial solvers to simulate these partial differential equations. It's more tricky to simulate accurately and efficiently. And it takes a lot of efforts. And in order to get a good solution, you probably want to buy a commercial software and actually run it and has a license. And you need to pay a lot of money in order to get that. Then the question is, can we do better? So for this, we actually have a very specific setting. We have a very specific like application in our mind, which is the antenna design problems. So in which we basically want to have an antenna that look like that. So people will say, oh, that doesn't seem to be an antenna. Antenna, in our impression, is that you have a bunch of like metal sticks like sticking out to the sky, and they put into different like arrangement so that it can receive some signals from the sky. Right? That's how our popular perception of antenna. But what happens in the real device is that you really want to put like antenna as small as possible. You put it into a very small piece, so that it will also receive strong electromagnetic waves from outside. That's the settings. So in order to do that, you basically want to design some kind of 2D PCB board, and you put like metals in kind of like a very magical layout, so that its frequency response will have specific forms. Right? So for specific frequencies, it will have super strong absorptions. And then you basically, by measuring the electric, by measuring the current or the voltage, you actually can read the signals out, and you can get the signals from other people. Right? So that's basically the design problems that you want to think about. So here, you basically want to find out what are the best arrangements of all the pieces so that the frequency response look like that. Right? That's the criteria. Okay, so usually before you get any frequency response, there's some target frequency response criteria. Say, okay, I want this frequency absorption to be frequency response to be lower than some threshold at some frequency. And you want that frequency response to be lower than threshold of some frequency. So basically, this is the criteria, and this is basically a very nice frequency response curve that will satisfy that criteria. Okay, that's basically the settings. Okay, so let's go back to the original problem. how can we really do something to this seem complicated equations, right? So in order to get any kind of interesting insights for this linear PDEs, we first discretize that into this form. Right? So we can actually show that for any linear PDE like that, after discretizing this with respect to the spatial domain, you can always write this in the following form. Right? So here's like one example. So you have so you have these wave equations, and then that wave equation has this Laplace operators. And this is on the spatial domain, right? So you basically do a discretization on the spatial domain so that the Laplacian operator becomes a linear operator, which is B. Right? And also you can decompose this second order temporal partial differential operator into two first order ones. Right? So by writing like 2x of these equations, and then you basically arrive at this A. Right? This A has this kind of interesting forms. And then this corresponds to the spatial discretization of linear PDEs. Okay, so once you have that, then we actually were going to prove a theorem that actually will tell you the property of the frequency in the frequency domain for the linear partial differential equations. So for frequency domain, and people might get familiar if you have any electric engineering background, right? So you basically try to convert this temporal signals using Fourier transform, and you basically convert this phi xt into phi x omega. Omega is the frequency you want to capture. So once you have representation of the frequency domain, then you have a theorem. The theorem basically says for any linear PDE, partial differential equations, right? So you can basically capture the signals at every location of your PDE. Then you can, for any kind of ratio of these two linear combination of the frequency domain signals, and they always have specific parametric forms. Right? So here the theorem basically says the ratio of the two is a ratio of polynomials, complex polynomials. Right? So we can prove this is true. And because it's a ratio of complex polynomials, you can always write them down as a product of multiple first linear kind of factors. So this is done by fundamental theorem of algebra. Right? So you can basically always write this that way. So you don't really know what is C0, what is Z, and what is P. They are actually some parameters that is magic. We don't really know what it is, but at least we know this is the form that we fall into. Okay. So any thoughts, any idea, any questions?
2 minutes.
Oh, 2 minutes. Okay, sorry. Okay, so if you don't have more questions, then we try to apply this theorem to antenna optimization. So the frequency response has a terminology called scattering coefficients. It actually has a form that is actually also a rational form of two equations. And then you can actually apply this form, you can actually arrive at this following parametric form of this frequency response. Right? So it basically has taken this form. Right? So you have Z0 and you have Z and P in its numerator and denominators. Okay, so this actually triggers to these following thinkings. Okay, maybe we should directly predict these three numbers, these three like family of coefficients that will be useful for determining the final like a parametric form of the frequency response, right? So in order to do that, we basically like learn a mapping from the image-based representation of the design choice all the way to these three quantities, right? That mapping can be very complicated. So we leverage the power of a neural network to learn these mappings from the representation all the way to these three two quantities that we don't know, but it can be critical for determining the final frequency response. Okay, so that's basically the idea. Okay, so once we have the idea, then we need to collect data. Right? So data is actually collected by commercial software. So we just like put this antenna design in the software, and then software will tell you the frequency response. And then we can basically do evaluations given this data and then the models. Right? So we can first do a static evaluation, which means that we have a held data set for all the input output, and then we try to test whether the surrogate model learned by neural network is actually accurate. Right? So we want to basically see like, what is the loss functions, how much is the loss. That's static evaluations. But more importantly, we also want to check whether the learned surrogate model can be useful for finding the design of an antenna. We just plug in the surrogate model into the search paradigm, which is actually powered by reinforcement learning procedure. And then once with the search give you optimal solution, you basically want to check whether the solution is really satisfying the criteria specified by the initial plan by the commercial software. Right. So and then we show some results. Like so, the static evaluation, we actually see that our approach that use transformers and images as input, and actually has a much lower errors compared to the baselines. Right, so this baseline includes a lot of very simple baselines. For example, we just use multi-layer perception plus the coordinate of the antenna piece as the input and try to predict the frequency response. Right, this is not great, but this one is actually much lower in terms of the errors. Right, so you have like a 50% error reductions, and we also test like this CDP framework, right? So here's basically the CDP structures. If you have a CDP, this model, that is, we basically like propose with theoretical guarantees, we see that the error is actually lower than the corresponding raw models that does not really use our CDP formulations. Right? So the raw model basically directly predict the frequency response rather than using the zero and poles as the parameterization. In terms of visualization, you will see that the raw prediction is actually very jaggy, right? So you see like a lot of like discontinuous structures there, because the raw prediction does not utilize the structure of the frequency response that is basically proven by our theorem. But our CDP model actually predict like something that is super smooth, right? So actually also is consistent with the actual simulations. So, and also, we also try these dynamic evaluations, right? So we are plugging the CDP model with search and see whether it actually gives you better performance. Yeah, the answer is yes. So if you compare this with the raw models, you'll see that our CDP model has higher successful rate to finding the good, in finding like a good design problems after the search technique. Right, so here we basically try 3 models, and each model has 3 search attempts. Using different random seeds, right? So, and then for each of the attempts, we basically check like if any of the top 3 solutions is a feasible solution according to criteria. And we see that with more and more data, both of them, of course, will have higher successful rate, but CDP model actually does better in terms of successful rate compared to the raw models. Okay, so the future work is that how we can apply this formulation to maybe more general linear PDEs, because the theory does not prevent you from doing that. Right, and we may also want to test on like more complicated scenarios like 3D structured antenna, etc., and maybe like other kind of design problems. Okay, so that's the talk. I hope if you have more questions, let me know. Yeah, I'm running out of time. Thanks for the attention.